Okay, we're on. Okay, thank you for attending my talk on Java 8 lambdas in the stream. I'm going to get into detail on how streams actually work, what's going on underneath the covers, and how you might get the best performance out of stuff like that. So hopefully it's a reasonably technical talk, and hopefully you'll come away with, this is quite interesting stuff. We've done a lot of interesting stuff underneath, and it'll give you a better idea of how to get the best out of this API. So some obligatory legal stuff beforehand, which you don't really need to know about, except just don't place any bets on what I say. Okay, so goals of this presentation, I'm going to introduce a bit about streams. Java 8 introduces lambda expressions, and among one of the benefits of this, it enables better libraries, and what's come out of this is the Streams API. It's a great example of how to use lambda expressions. So you're going to learn how these lambda expressions going to be used in the Streams API. You're going to understand how to get the best out of it. But also, this is one of many potential improvements to Java going forward. It's an improvement both in how you use and design APIs, but it's also a performance improvement. And going forward from 8, 9, 10, 11, there could be many other potential improvements to enhance what we've done already. So streams are really about aggregate operations. You've got lots and lots of code out there which does sort of queries on data, often using collections and loops. And usually you'd write this in a sequential way, fundamentally, and also an imperative way, which can be quite frustrating. So Java 8 answer to this is the Streams API with a little bit of help, or quite a lot of help, from lambdas. So here's a very, very basic example. We have an imperative example here, which is basically get me all the transactions and all the buyers in the state of New York and sum up the price of those transactions. Here we see a simple for loop doing that over an iterator, over a collection of transactions. And here we see the equivalent in the Streams API. We say we filter based on the buyers who live in the state of New York. We map to an int on the price, and then we sum it all up. And you might say, well, okay, I like my for loop. It looks pretty good. There's not much difference in the number of lines we're actually doing here. But what we've done already, we've upped the level of abstraction here. And once we up the level of abstraction, that gives us a lot of maneuver underneath the covers to do things differently. So instead of a sequential stream, we can now go parallel. So what might be happening underneath the covers is very, very different to what it was when it was a sequential stream. But because we've upped the level of abstraction, and now we're passing behavior to these filters and these map methods as functions, these lambda expressions here, we can do lots of different and interesting things underneath the covers. And as well, even in this very simple example, I would argue that there is a readability aspect to the bottom one that is not quite so clear in the above one. Here's a more complex one. How many of you saw this in Brian's keynote talk? How many of you grokked it immediately? Not many. I'm not going to give you time to grok it. But if you just look at it, there's a whole bunch of noise in here. I've highlighted the red bits in what is kind of interesting here. You're staring at it. This is not uncommon code. It's not the most optimal way to write this code, perhaps, but it's not uncommon. But there's all sorts of bits that are interesting, and you have to remove the noise to sort of get at the bits that are interesting. But in a lambda and a streams way, it becomes a lot more like a sort of set of statements, a set of what you do, not how do you actually do it. The above one conflates the how with the what. It's saying, how do we loop over it? Where do we stuff stuff in? We've got a load of garbage variables and all sorts of stuff. But the one below sort of says, I want to filter based on the age of my buyers. I want to then map it to the sellers. I want to get all the unique sellers. Then I want to sort on it based on the seller's name. And then I want to just print it out. It reads like a problem statement as you go through. You can make some improvement on that. You can use something called method references, which can even improve the readability as you go forward. But I hope you get, just from this simple example, as soon as you sort of scale up, the advantages become more and more apparent in terms of the readability of your code. And plus, you get the parallelism aspect as well, without having to change any of your other code underneath here. So here's a table expressing what I sort of talked about before. So it focuses on the how, the imperative case. We focus on the what. We're not trying to conflate the two together. And it's much more factored than before, where it's all mashed together. There's no garbage. You notice in the old code there's lots of garbage variables around. We don't show what those are. And the important thing is that the former one is inherently sequential. If you want to parallelize that, you'd either have to have a very clever compiler that works out from your imperative code how to parallelize those loops underneath the covers without telling you, or you have to start using fork join, which will make your code go like that. So what is a stream at a high level? It's really just an abstraction for specifying aggregate computation. It's not a data structure. In a sense, it's a bit like an iterator. An iterator is not a data structure, and it can be infinite. It's not restricted to the size of the data in infinite form at all. And it really, as I said, up the levels of abstractions of your computations, and that is really key to exposing the levels of optimization we want to apply. Not just for parallel, but it gives us the room to maneuver underneath the covers in the future, both in sequential operation. We could do some potentially very interesting things in the future to optimize that. And it allows you to take this pipeline and essentially fuse it all together, apply laziness, out of order execution, all sorts of stuff like that, because we've upped the level. In a sense, it's the mantra of you can solve anything in computer science with another level of indirection. So let's get a bit more detail of how how a stream or a stream pipeline is composed. So it really consists of three things. We have our stream source. So if you look at the collections API, we now have a new method on collections called stream, and we call that the bun method. When you eat a burger, you have to get through the sort of bread to get to the good bit, that's the meat. So that we essentially transform or transition from our collection into a stream. And this is the source of our stream. It's where we get our elements from. So our stream covers a bunch of elements. If it's an array list, it will cover all the elements that are held in that array in the array list. Then we have 1, 0, or more intermediate operations. So here we have two intermediate operations, a filter and a map to int. And then we have a terminal operation, for each, reduce, or sum, and this produces the result or a side effect. So what about execution here? What actually happens when we call the filter, the map to int, and the sum? So the filter and map don't actually do any work at all, in the sense of actually operating on the elements. What they do is that they build up the recipe of the pipeline. So when you call filter, no work's done. We don't copy all the elements from our stream source and remove all the ones that we don't want and internally hold those in an array or an alternative representation. We don't then operate on the map and create a new piece of data at all. It's entirely lazy building up a recipe. And then when we hit the sum operation, the terminal operation, that's when all the work happens. That's when we kick in and we can go either calculate all this sequentially or do everything we can in parallel. And the key thing here is this filter map reduce. It's all compressed down into one operation. We pump elements through, filter map it, and sum it. Each one goes through the pipeline like that, and we fuse it into one pass for both sequential and parallel pipelines. So execution only happens once. We cannot branch or reuse pipelines, and this gets it across here. If I break down the expression from a fluent expression and assign each stream to a separate variable, we get our stream from our transactions, and then we filter it, we get a new stream. But once we operate on the stream S1, we can't operate on it again. We get an illegal state exception if we operate it. Likewise, when we transform stream S1 using filter into a filtered stream S2, we can't operate on S1 anymore. And so on until we get to the terminal operation we call S3.sum, we can't operate on S3 anymore. So it gives a very simple model to understand. You can't do any complex branching, and it simplifies the implementation as well, I think, simplifies how you use these things. So there are many, many ways to create streams. One way is to use the existing collections in JDK or arrays. We have done a lot of work to all the existing collection implementations in the JDK, both the array list, hash map, so forth like that, and also the concurrent collections. you can also get a stream from. There's a big thanks to Doug Lee here. Without him, I don't think we would have completed this work. From what you see, just looking at the surface area of the API of streams, it's actually very small, four or five interfaces. But there's a lot going on underneath the covers here. There's a lot of implementation work that's had to happen to realize this. You can also get these from streams from factories like a range, or from, say, the files class, or from a buffered reader and so forth. When you look at classes in the JDK, one thing you should look at is the methods and see which ones return stream as an indicator of what you can use. Or you can roll your own stream sources using something called a splitterator, which I'll get onto later, which is really the key abstraction underlying a stream source. This is a key thing that allows you to traverse elements and allows you to decompose your source into separate parts that then you can actually operate on in parallel. So a splitterator, splitting and iterating combined together. So what about stream sources? Like stream pipelines, they have three aspects to them. You access the stream elements for a source. It allows you to decompose via a splitterator into separate parts. And it also has a bunch of characteristics associated with it. You can see how it's kind of like an iterator for the first bit, but we add a lot more to it in the decomposition and stream characteristics. And these characteristics, you can say that I know the size of my stream. When I'm dealing with an array list, I know the size of it. If I'm dealing with an infinite source, I don't know the size of it. There's a characteristic called ordered, which says, does my stream have an encounter order? So a list will have a well-defined order when elements should occur when you iterate or traverse over them, whereas a hash set doesn't have any order whatsoever. The elements can come in any way they like. That is important when it comes to parallel execution, not so much for sequential, but how many people have depended on the iteration order of a set or a hash set by mistake and then found it might break later on? We broke the JDK by doing just that with introducing sort of different hashing functions in the JDK, and it broke some code because people depended on the order things going for a set, which we shouldn't do. There's other operations like distinct. Are all the elements in my source distinct, like in a set, or are they sorted, like in a sorted set? These are important because these characteristics give you the ability to optimize the pipeline as you're building it and also as you're executing the terminal operation. So here's a table of a bunch of sources, the quality of decomposition and the characteristics. Decomposability is important for parallel operation, but also how you decompose. If you decompose in a balanced fashion, say I split my array list up into 4 equal parts, that means I'm creating 4 equal pieces of work to operate on concurrently. If you split it up in a sort of unbalanced fashion, one thread may get more work than another thread, and you would not get the performance you might expect from it. So decomposability is an important aspect when you're selecting a stream source to build a pipeline from in terms of parallel operations. So an array list has excellent decomposability since its internal representation is array. We can split it in half, split it in quarters, split it in eighths very, very easily. It's sized and it's ordered. Whereas linked list has poor decomposability since we can only access an element from another element going through. It's inherently sequential, so we can't actually decompose it without actually copying a prefix of elements into an array and then operating on that concurrently, then sequentially copying another prefix and so on, and we essentially create what's called a right balanced tree, which means the computation is not balanced, which means we're going to get sort of not as good performance. But again, it's sized and ordered. A hash set has good decomposability because we have an array that's actually the table of a linked list of entries and keys. So we can get some reasonable decomposability from that, which is better than, say, a linked list. And it's sized and distinct. Int range is an interesting one. It's sized, distinct, sorted, and ordered, but it doesn't actually hold any data. It just produces elements as it goes. And then you can see some other cases like buffered reader, or a very interesting class that we added recently, splittable random, which is a new pseudo-random number generator developed by Guy Steele and Doug Lee that allows you to split your random number generators, but without actually sharing any state, but they share the same statistical properties in terms of the sequence of numbers they produce. I have an example. I can't show you it, but I have GitHub code that you can download and look at the use of that with a Monte Carlo simulation. So intermediate operations, as I said, are lazy. No work is actually done when you call a filter or a map, except building up the recipe for the pipeline. Importantly, they can affect the characteristics of the pipeline. I will get into more details in that on the next slide. And some parallelize and fuse much, much better than others. So there are some which are stateless, like map. Map should be a function of its input only. Same for filter, or same for a flat map like that. They're totally stateless, and you can fuse them all together really, really nicely. Whereas there's a couple of stateful operations, such as sorted, distinct, or limit. And these fuse or parallelize to varying degrees depending on the characteristics you're dealing with the pipeline. So sorted is essentially a barrier. You can't return the result from a sort until you have all the elements available to actually sort. Distinct can be a barrier. It depends. It depends if you're dealing already with a sorted stream, it can be more efficient. Limit can be a barrier or not. It depends based on the input coming in. So there's various optimizations we can apply here based on things. I'll get a bit more into detail of those. So say I have my stream source, which is an int stream of range from m to n, a bunch of numbers. So this has all the ticks for all these characteristics I've talked about. So it's sized, ordered, distinct, and sorted. And if I do a filter operation on that, I inherit or preserve the order, distinct, and sorted, but I lose my sized characteristic. I no longer know what the size of my stream actually is. That may or may not be important in terms of performance or not, but I can no longer apply my sized operations because I no longer know what the size of my stream is. If I do a map operation, I lose my distinct and sorted. I don't know how my elements are being transformed from one element to another element. It might be an identity transform, but I don't know that from looking at the code. So I lose my distinct and sorted, but I would inherit whatever the upstream pipeline had in terms of the sized and the order. We have an unordered operation, which all it does is cross off the ordered characteristic. This is important for parallel operations if you want to produce results in an unordered fashion rather than actually preserving order. But just for the purpose of this, it just crosses off the order but inherits everything else. But I can inject flags as well. So if I do the operation, intermediate operation distinct, it will re-inject distinct back into my stream. And sorted will re-inject ordered and sorted flags. Limit actually will preserve the ordered, distinct, and sorted, but actually in our implementation, it clears or cancels the size flag, which might seem a bit weird. I have a little asterisk on the next slide. I don't really want to go into why, but you would think intuitively that it shouldn't do that, but it does. And then we have an operation called peek, which essentially allows you to help debug your pipelines. It doesn't do anything in terms of the characteristics of the pipeline. It just allows you to look at what the elements are going through. So here's a table expressing what I just talked about there. There's an operation here called flat map, which is sort of like a fused map and a filter, which removes distinct, sorted, and sized. Sorted is interesting because it's a no-op if you're already sorted, and same for distinct. And also, if you're distinct and your stream is already sorted, you don't have to remember all the elements. You can just keep the last element that you remembered going through. So there's all sorts of interesting optimizations we can do. And limit is actually short-circuiting. So terminal operations execute the pipeline, and all operations can execute sequentially or in parallel. And like intermediate operations, we can take advantage of the pipeline characteristics. So if we do a two-array operation, we can avoid copying if we know that the pipeline is actually sized. And I'll show an example of that in more detail later on. So here's a summary of the various terminal operations we have. You can group them together in terms of aggregation operations like array, two-array, sum, min, max. The key important ones are reduce and collect, because many types of terminal operation are composed of reduce and collect. There's iteration using for each. This is interesting because if you're going parallel, this will not preserve the order of what you expected coming in to your input. And there's searching operations like find first or find any. And find any is non-deterministic when you're running in parallel because it just give me the first element that you can return me as fast as possible. So there's just a few restrictions here when you're using streams if you want to get the best out of it when going sequential and parallel. You shouldn't interfere with the source during execution. The reason is you're going to get strange results if you do, or you'll get one of these concurrent modification exceptions. How many of you have done iteration using a for and received a concurrent modification exception? They help. They're rare when they come, but they often help you debug the situation. So we've made sure that a lot of our implementations can support concurrent modification exception, even though it's a misnomer, because it doesn't really have anything to do with concurrency in terms of the way things are implemented. It's really more when you invert control that it catches things when you're monkeying around with a source when you shouldn't be. The really important thing is operation parameters. These lambdas we're passing into operations, they must be stateless. They should, for the most part, be stateless. We shouldn't interfere with state so that, say, a map function, its value changes based on something beyond that of its input. When you start doing stuff like that, it might work well sequentially, but as soon as you go parallel, you're going to start getting strange results. So it's really best to banish side effects completely. You're at risk from concurrency hazards as soon as you go parallel. And there is an exception to the rule. For operations like for each or peak, they accept a consumer interface, and a consumer returns void and accepts a T. So the only thing you can do is operate by side effects on that. So you should, when you're using pipelines with for each in, you need to be aware that if you want to retain the parallel and sequential nature of stuff, that for each could be called concurrently. So you need to be careful of what you do there. So here's an example of why. So say we have a list of T, and we map it, and then we for each on it, and then we add each element in my stream to the list R, like that. If I run that in parallel, how many people would think there's an issue with that? Please, all hands raised up. There should be an issue with that, because if you run that in parallel, our list may not be thread safe. So we could have an issue there. It also may not preserve the order of our input, because the elements that will occur will be reported to the consumer of a for each can occur whenever a thread is ready to report it. So it's best to replace it with a collect operation with a collectors to list, which is thread safe. And interestingly, it allows us to build up parallel operations on something internally that might not actually be thread safe like an array list, but there's ways we can ensure we can do that using collectors. So the key thing here is there's almost always a way you can do what you want to do without statefulness or side effects. You just have to sort of shift your thinking slightly. One of the key tools that you use to do this is reduction. So reduction is essentially or what some people call a fold, or if you listen to that how to do parallelism not, that great Guy Steele talk, catamorphism, did I say that? So some min-max count are special cases of reduction. You can reduce these cases down to reduction if you want. So often what they will do is you reduce a bunch of elements down to a single summary value by using a combining function. Now that summary value doesn't have to be a scalar. It could be a list. It could be a set. It doesn't matter. It's just reducing the bunch of elements might have to something else. A key aspect of reduction is identity and associativity. So those things you learned in high school, they're now useful now. So sum is a reduction essentially with a base or identity value of 0 and a combining function of plus. So the example we see here is 0 plus A1 plus A2. That's essentially, if you're familiar with something like that, feels like a fold left. I'm starting with 0, I'm adding 1, and then I'm adding that, adding A2 to that, adding A3, and so forth like that. And sum in the Stream API is essentially a reduction with a base value of 0 and a lambda which adds the two numbers together. Or if you're using a method reference, it will be integer : : sum, like that. And you can implement a count method which says how many elements do I have in my stream as essentially a map reduce. I map each of my element to 1, and then I sum it, which is essentially a reduction like that. This is what I was talking about. There's almost always a way to avoid state or statefulness. And one of the key transitions that's useful to make is that map reduce is actually quite powerful here. So the key thing also is if the combining function here is associative, reduction parallelizes cleanly. So in the example here, I have the grouping towards the left, but it's also equivalent to the grouping on the right. As long as I don't monkey around with the order of my terms A1 to A4, I can group them in any way I like and still get the same results. So on the right-hand side, I've grouped them in a balanced fashion. So I can take the A1 and A2 and the A3 and A4 and operate on them in parallel and then sum up the result sequentially afterwards. That is the key thing that allows you to decompose properly with reduction. So here's an example of reduction going on sequentially. So we have our base value of 0, and we're just going to fold all our numbers in one by one by pushing them through the stream as we go to get our result like that. So all the elements just flow through the pipeline, and we just keep stuffing them into the box, which just accumulates them. So if we had a filter here, to get across the idea of what's going on with fusing, we're going to filter all elements so that we're going to drop the first two elements, essentially. So instead of them going into the box, they just get dropped off as we go through the fuse pipeline, and all the rest of them get stuffed into the box like that. And that's sequential reduction. It's actually fairly straightforward. So some reduction targets are just not scalar or do not scale. So if you're going to reduce or fold elements into a list or set, this is how you would do it using the pure reduce form and using MapReduce. So if I had a stream of elements, first I'd map each element to a singleton set, and then I would reduce all those sets down to one big set, like so. So my base value here has to be the empty set that I start with, and then my combining function has to copy all the elements from my old set of these two sets together and return it. That is extremely inefficient. That's not going to work with our existing Java data structures. We don't have immutable collections or persistent collections in Java yet. How many people would like persistent immutable collections? I would. If we had those, we could use those with this kind of style and maybe get better performance. But if we're going to use array list or a hash set, this is going to suck. So we need an alternative. And that's mutable reduction is a collect. So like I showed before, there's a collectors.toList. So, and it basically takes a collector, and a collector is a recipe for organizing desired results in a desired form. It's actually very powerful, but it's the way you, say, transform or you reduce stuff down to a list, to a set, and so forth. There's a lot more to it I don't have time to get into. There are many, many of them available. Here's two examples. So I have a stream, I want to filter it, I want to collect it to a list I call collect.collectors2list, and you can use the static import if you want to not have to type collectors in all the time. Another example, I want to collect to a histogram, so a map of t to integer. There's something called grouping by, which says map my elements to keys, then map each element that maps to the same key, reduce all those down to another value. So it's essentially like a sort of a reduction, but only on the key. I'm only reducing values that always associate with the same key. It's like a layered reduction, if you like. So I can create a histogram by saying grouping by, function identity, and counting. And here I've used the static import. Grouping by and counting are collectors on the collectors class there. So this is actually a very powerful mechanism. And again, it works in sequential or parallel. So I'll get in a bit more detail about parallel streams now, why this is important and how to get the best out of it, and to sort of perhaps dispel some myths about it. So the key reason why you want to go parallel is performance. That is really the only reason why you might want to do it in this case. There are many, many chips and many cores per machine, but each of them is not getting much faster. So we need to take advantage of all these cores and keep them all hot. There's also GPUs as well, which are sort of on the side of CPUs, or being put into the same chip as a CPU as well. And there's a very interesting project called Sumatra in OpenJDK that you can look at that's trying to apply streams to the GPUs and executing stream pipelines on the GPUs themselves. And GPUs with like over 100,000 cores, little tiny 1,000 cores inside them. It's really quite interesting. And fork join is a really great API, but it's way, way too low level to code against. The amount of code that you need to do the same thing as what you want to do in the Stream API with fork join is huge. So Streams uses the fork join API underneath to get the benefits of parallelism. And fork join in Java 8 has been improved quite a bit by Doug Lee. One of the key things you need to know about is many things will affect performance. The size of the data you're dealing with, how well it decomposes. Like I said, with the stream sources, some things decompose better than others. A better decomposing source will parallelize better than one that doesn't decompose very well, say like a linked list or an iterator. There's the number of cores you might have as well, and there's also the cost per element. How much does it cost to process an element going through the pipeline? That's a key factor too. So sadly, it's not a magic bullet. We've given you this parallel, but it's not always faster. But it's a way to get the speed if you want it, and if you do things right. So you can think of parallel streams as MapReduce in the small. We've got Hadoop MapReduce in the big, but it's actually conceptually not really very different. In MapReduce in the big, usually the map bit also does a reduction bit too. And in fact, you could use streams on the leaf nodes of Hadoop to do even further parallelism, taking advantage of fork join if you wanted to. So a key thing is we've made it explicit but unobtrusive. So you have to opt in to going parallel. Sequential is always a default. Parallelism may be faster, but one of the things it does is it introduces non-determinism. We try and hide that, but in some cases we expose it out. So a stream pipeline is created with an orientation of either sequential or parallel. We don't split parts in parallel or split parts in sequential. It's either sort of a bit on the pipeline. I'm sequential, I'm parallel. The last call to either one of those actually wins. Before we had this sort of staging between sequential and parallel, and it just got complicated. We just simplified it down. It's either parallel, sequential, last call wins. So what we try to do is sort of have the sort of maxim of element of least surprise here. So where possible, the results should be deterministic unless we state otherwise. So when you transition from going from sequential to parallel, you shouldn't, for the most part, expect any surprises, at least in terms of the results that are produced. So here I have an example of collecting two lists from a stream. So we have stream map collect, and we have stream parallel stream map collect. How many people think those lists, those two lists, should be equal? How many would like them to be equal? Everybody? Yeah, that's the right answer. They should actually be equal. If we exposed out a different way, if we changed the way our implementation works, so we didn't care about the order of list. List has an encounter order. That's important information. If we ignored that and the lists you got back there are differently, we're sort of introducing a bit of non-determinism into the result there, and that will cause some surprises. Now, if these two things were sets, that would be different because set doesn't have an order. You shouldn't be depending on an order when you're dealing or processing sets. That's okay. Here's a non-deterministic example where we expose out explicitly. We have a stream, we filter it, and we just want to get any element from the stream. We don't care. If we do it sequentially, the reasonable choice would be the first element that occurs in the stream. But if we go parallel stream, it might not be the first element. It's whatever the thread that got executed first for its bit, its first element, from the decomposed stream, its first element, it might win and return it. So it might not be the first element. So asserting that E1 equals E2 may actually fail. The only assertion you can make that E1 and E2 were in the original stream and were actually the filter actually passed. So let's look a bit more into actually what's going on underneath the covers and how it decomposes and how parallelism actually works. So what we do is essentially, it's the classic divide and conquer. We have a parallel pipeline and it's decomposed essentially into many sub-pipelines. So we have a big S, which is a stream pipeline, a stream source you want to do. We're going to map and sum it. We essentially split it up or decompose it into four. Say we've got 4 cores. We decompose it into 4 little pipelines, S1 to S4. And then we operate sequentially on each of those 4 pipelines concurrently, in parallel. And we get 4 little results, R1 to R4. And then we have to merge all those little results back together using sum again and produce our big result as we go through. So we split it up, operate sequentially, and then merge it all back together again. Now the problem is, when we do this, it's almost always more work to split this up and to merge it all back together again. But because we're operating on this in parallel, it might be more work, but we actually complete it faster. So it's a battle against Amdahl's law here. It's a battle against the decomposition and merge costs. If we got cheap, efficient decomposition and cheap, efficient merge, we might win. The key thing here is for small and simple problems, sequential is still usually faster. That cost of splitting up, warming up all the threads to execute on it, managing the way the results get all merged back together again, it might not work for small pipelines. And the key thing here, this is back to the statelessness in the fine print. You can see now these lambdas highlighted in red. We're taking the same lambda we had on our big stream, and now we're running it sequentially and concurrently on all our little streams. So that lambda expression could be a function, could be a predicate, is going to get invoked concurrently. In any order, elements will come in whenever threads are ready to call it. And that's the key reason why you want these things to be statelessness, and have no state associated with them if at all possible. Because if you do, things are going to get strange when you go parallel. It might work sequentially, but when you go parallel, it's going to fail. Now, unfortunately, we can't detect when something, a lambda, is stateless or not. Currently, I don't know if it's ever possible at all. So it's up to you to make sure that these things are stateless to get the best out of going parallel. So I explained how things are sort of split up and then merged back together at a very high level. This is actually what's happening a bit more under the covers. So how do we execute, say, a range of numbers from 1 to 8 parallel and then sum them all up like that? So we have a source of elements which go from 1 to 8 here. And we essentially want to split this in two. Range has great decomposition, so we split it into 2. And then we can split it into 4 again. And then we decide there's no point splitting anymore because the cost of more splitting is going to take more work and we won't get any benefit from going parallel because we'll end up being slower than sequential. So now we've got these 4 leaves and we want to operate on these 4 leaves in parallel and sum them all up. See, before I actually explain what's going on now, I just want to show you how it's grouped. We can see now how we group these summations into brackets. So we've separated them all out and we can. This is the key idea of why things are important to be associative here. We can actually group it separately. As long as we don't monkey around with the order of the terms, we can group it. Our results should come fine. So say one task completes here, and then another task completes, and then another task completes here. Now we've got 2 tasks of a parent actually finished. So the thread that completed the summation of 1 to 2 can actually complete the parent task as well. And then another task completes, and now the parent has 2 tasks that are complete, so it can sum it up on the same thread, and then the same thread again can sum up to get the actual resulting value there. Now what I showed with these nodes is that those are actually correspond to fork join tasks, a specifically counted completer in fork join, which is introduced into Java 8. So that's essentially we build up a computation tree, and then we merge back up the computation tree to produce a result. Now, to get across the idea of what this base value actually means that I talked about before, being 0, say we added a filter operation here, and I've exposed out my sum as a reduce. The first 2 leaves now have no elements in whatsoever, so we need an initial value to say what it is we're going to be summing up when we merge up the tree. And you can see why that initial value now has to be 0. If it's 1, it's going to basically produce a result based on the depth of the computation tree is. If you've played with streams, how many of you have messed around with this base value and got strange results when you've gone parallel? Has anyone actually done that and sort of went, ooh, that's a little odd? This has to be a base value, an identity value, so 0 plus anything is the same value. That's the key thing. So when I showed the reduce to an empty reduction, not a pure reduction for sets, that's why I chose the empty set there. Here's an example taking advantage of the sized characteristic that I talked about earlier. So we have a range from 1 to 8 parallel, and we're mapping it to the square, and we're creating an array from it. So we know that we're not changing the size of our stream. The size of the output should be 8 as well. So we can split it in exactly the same way, but instead we can actually make room for an array of 8 elements here. We're going to stuff our elements in there. And then we can know the indexes into that array. We can stuff things in as we generate the computation tree. And then we can stuff elements into the right index into this shared array, and we can do it concurrently, like so. And we don't actually need to merge back up the tree and like copy lots of little arrays together as we go up, so we can actually get a speed boost, and this is because we know the pipeline is sized. So performance-wise, you should ask the question, should I go parallel? But you shouldn't assume that parallel is always faster. It's easy to do, but not necessarily the right thing to do. There's a bunch of qualitative considerations, like how good is your stream source decomposition I talked about. Is the merge step or the combining step an expensive or a cheap one? And what are my stream characteristics? Like with 2Array, I knew that I was sized, I can be faster that way. We've also introduced primitive streams included for performance reasons because of boxing. It hurts. I'll try and explain that in a bit. So there's also quantitative considerations. There's quite a simple performance model you can think about. If you think about n as the size of your source data set, you can think of q as the cost of processing one element through the pipeline. Then the cost of the pipeline itself is approximately n times q. The larger that is, the higher the likelihood you're going to get good parallel performance. And it's very easy to know n, but it's not quite so easy to know q, but you can sort of reason about it qualitatively, what it might actually be. So for small data sets, when n is small, sequential usually wins, unless q is very high. And in simple pipelines, it's often easier to guesstimate what q is. Do you have 10K elements or more, for example? For complex pipelines, it's harder. If your source is derived from an iterator, if it contains a limit or a grouping by, these are warning signs that you may not, it's complex to sort of reason about what the performance results might be. Now, if in doubt, measure. That's the key thing. The problem is the JVM is very dynamic. You might not realize what is actually going on under the covers. It's moving code around, compiling, doing GC, all stuff like that. This can affect your measurements in surprising ways. And it's best to use a benchmark tool such as the Java measurement harness to try and help you get the best out of that, because it will try and make sure that the hotspot doesn't do funny things under the covers while you're actually measuring. So I'm going to go through probably just one example. I'm running out of time. I'm going to show a low Q example of a map and sum. I have these on GitHub. You can download and actually execute and try them out and experiment with these JMH examples. So I'm going to just pop into IntelliJ here. And just show it. So I have a very, very simple JMH benchmark that I want to measure, which is essentially, can you all read that? Yeah, it looks big enough. I want to measure the difference between summing based on a loop and summing using a parallel stream and summing using a sequential stream. Now, I've been quite good. I'm using JMH here. I'm using a micro benchmark harness. Everything looks great. Now, let's go and actually measure that and see what actually happens. So I've got this set up to actually run with some So I'm doing this quickly. You wouldn't normally do this with JMH to get the results. You'd run it for a lot longer, but it actually shows the anomaly I want to explain. Even when you're using a micro benchmark tool, you have to be sometimes careful about what's going on. So the results that come up here, I've got my loop, parallel, and sequential, and I've got some numbers here. The loop and parallel look pretty straightforward. The 44 microseconds per op, 42 for parallel. This is for 100,000 elements I'm summing up. But look at the sequential, it's way off base. What the heck's going on there? That's not right. So even the simplest pipeline, when you measure it, it might not give you what you expect, so you have to be careful. If I actually look at this a bit more closely, what's actually going on? So I'm just running the sequential version here. We can see that after a bunch of iterations in JMH, it looks good. I'm getting 55, 53, 54 microseconds per op, and then suddenly, poof, I've lost, there's an order of magnitude drop in performance going on. What the heck happened there? This is time to scratch your head. This is a VM doing mysterious stuff on us. So what the heck is going on? Well, if you look at it, I'm doing about 55 microseconds per op. I'm running each iteration for 50 milliseconds. About iteration 6 or 7, that's about 10,000 iterations. That is when the hotspot will start compiling stuff, when a method has been called 10,000 times. What's happening here is the hotspot is compiling the sum method, the int-stream sum method, and de-optimizing my hot loop that had been optimized before. That's strange. Shouldn't be doing that, but that's what inlining actually does. So I can actually show what's actually going on here. I can actually disable the compilation of the int-stream sum method and run that again. And we can see that, look, it's excluding a compilation of int pipeline sum, int-stream sum, and I get the similar performance levels as to what I had with the parallel and with the parallel and the loop. The key thing here is that the depth of inlining that I have in my VM is too small. If I up the inlining level of my VM and change a flag to my, oops, sorry, that's wrong one. If I just run this and change my max inlining threshold from 10 to 11, then I get the performance numbers that I want here. So you just have to be careful in this because it's a very simple pipeline. There's a lot of room for optimization in the hotspot and inlining, so you've got to watch out. This is something that in the future means we've got a lot of work ahead of us to try and inline streams better than what we do now. We shouldn't be inlining and de-optimizing our hot loop over all these over the streams. So there's some interesting work ahead in the future, but hopefully that gives you a little feel when you're measuring. You have to be a little bit careful about what's going on. Okay, back to the slides. So I may come back to this one if I have some time. I have some more slides to go. I might pop back up to it. But there's a bunch of ones here showing the cost of boxing and using primitives, showing a Monte Carlo calculation of pi using splittable random, and showing megamorphic call sites. And it's very easy to experiment and sort of see the differences in performance you might get using a tool like JM8. It's actually really good. Simple examples on GitHub if you want to try it out for yourself and experiment measuring streams to see if you get the benefit from parallel or sequential. So here's some performance results I got using JMH properly over a long period of time. Of map and sum and int compared to, so I'm comparing to the speed up over the loop implementation here. And we can see as n gets larger, the sequential reaches close to what the performance of the loop implementation. So you see, when we go to streams, we're not going to be as fast as the tight loops. Hotspot can easily optimize those tight loops away. We can't optimize those sequential streams away in the same way yet. We might be able to in the future, I don't know. We can see the parallel, gosh, the parallel performance sucks. Look at N10, 100, it's really crap. But as n starts to grow bigger and bigger and bigger, we start to, you see this sort of S-curve as n gets bigger and bigger. But Q is very small, so we need a lot more elements so that this splitting and merging actually we can overcome that actual cost. So the crossover point is between 10,000 and 100,000. I said approximately 10K, so it's sort of in the ballpark. And then we get over that and we reach sort of 1 million, 10 million, and we start to get to the sort of the speed up you would expect on the system I actually run. That's a common pattern you should see with low Q. So I'm just going to skip the big integer one for now and talk about the case for boxing. So we introduced primitive streams like int stream entirely for performance reasons. Say I've got an int array here, and I can decompose my int array very easily and say each of these colors corresponds to a thread that's executing on this int array. And they can get access to these elements very easy. It's all nicely cached close to the core that's actually running. I don't need to go out to main memory for each element because I've sort of got a bulk content. I bulk loaded it close to my core, and I can get it in my cache, which is very fast compared to going out to memory. But as soon as you go to integer array, you're not dealing with that. You've got a bunch of boxes instead. And your numbers are all over the place, potentially all over the place in memory. And so you're going to have to follow the pointer and follow the pointer, and that just blows your cache coherency apart. And it's even worse when you've got a pair of integer-integer. It's another level of indirection. So this is what people refer to when they're pointer chasing, and your performance in parallel nosedives because of that. So the case for value types, this is my dream, is rather than pair integer-integer, why can't I have an array of pair int? And pair becomes a value type with no identity. And what that means is underneath the covers, the VM can optimize this. So it doesn't have a place. It just has, it's just a value. I can unpack it. I can sort of deal with it all as one big array as a representation internally in the VM. And then it all gets nicely cached, and each thread can operate on it efficiently. That's one key thing you can get from value types in this way. And that's very interesting optimization, but it requires a lot of work, future work in the VM, in arrays. What's a value type? How do we express those out? How do we reify ints and so forth like that? There's a heck of a lot of work to do. And if I put on my tinfoil hat even further, pure speculation, what if we can have a stream of pair int? That could be a complex or a tuple. If I could map and filter it underneath the covers, what if Hotspot could sort of unbox those lambdas? Instead of P, I deal directly with the actual ints of X and Y directly, and Hotspot works out how to do that and inlines the whole thing, and I can get super sequential and parallel performance out of that. That's a long way off, but that's my dream. It would be cool to get that. Okay, so making streams, we have a spectrum of options here. We can get them from a collection. Often that would be your first choice when you get a stream. You call array list stream and so forth like that. You can have static factories, stream ob to create an array or a list of elements, stream range I've shown before, or you can do it from an iterator if you really want to. Not the best thing to do. We've made it kind of difficult to do that. You need this long expression to actually generate it from an iterator yourself, but you can do so. Or you can create a poorly advancing splitterator. Essentially, we provide some solutions for you. If you want to provide characteristics of your stream source, this is what you would use, and you don't have to implement the decomposition yourself. Or you could implement an optimally splitting splitterator, and this is where you get the performance for your data structure. We've implemented optimally splitting splitterators for all the JDK collections, including the concurrent ones as well. So splitterator is essentially a parallel analog of iterator. It's an abstraction for decomposing our data. It's the key abstraction underneath streams to hook it in. It's actually quite simple but powerful. It reports the characteristics that we see in our stream source, like size, distinct, and ordered, but there's also a bunch of other ones like concurrent, immutable, non-null, and subsized. Subsized is an optimization of sized. And JDK collections come with a whole bunch of them that are useful. So here's the code for splitterator here. We can group it into 3 types of things. We have our traversal methods, we have our splitting methods, and we have our properties. And it's a way, way better iterator. If you think of iterator, it's a pain in the backside to write these bloody things. You know, you've got the has next and next. When you implement your iterator, you've got to, and usually often the way you do it in next, you call has next to make sure that you're in the right state. And when you iterate over it, you call has next before you has next. So there's a bunch of calls going on, which is just a waste. So we have a try advance method that is much more efficient than what you do with iterator. And we have a for each remaining method that allows you to deal with it in bulk. And there's a bunch of properties and the splitting and so forth like that. The key thing here is this action on the splitterator. We pass an instance of consumer that represents our fused operations to splitterator. And then splitterator operates by passing elements to the consumer. And this is actually a problem because it turns into a megamorphic call site, which basically means that there's lots of different types get called here, and it gets harder for the hotspot to optimize. So this is a key thing we need to optimize in the future going forward. So how do we decompose, given an array list? So we've got an array list which covers a bunch of elements. If we get a splitterator from it, it covers the whole elements. It's kind of like an iterator. If we split that, it splits it in 2. The splitterator that we had gets shuffled up to the rightmost elements, and we create a new splitterator covering the leftmost elements here of the list. We split it in half. We can split it again, like that. It's actually quite an efficient data structure. We don't create two new split arrays. We morph one split array into another one as we keep going and how we're splitting. So we can split an array list very easily. Just like we decomposed our tree, every time I showed that sum decomposition, we split our split iterator as we go through the int range or an array list, like that. So how does it work for a hash set? So it's a little bit different for a hash set because we're dealing with a table of our sort of key value entries. We can't split it in the same way as an array list because we don't have that data easily available to decompose efficiently. But what we do have is essentially a hash table. So we can have a hash table which might have a linked list of entries in there corresponding to the same key, or it might be a red-black tree. So we can split on that table instead. So at the start, we can split, we cover all the elements here, and we know its size and so forth. But once we split, we might not know its size anymore because we're splitting on the table, we're not splitting on the elements themselves. So what we rely on is a good hashing algorithm so that values are distributed equally or approximately equally over the hash table. So we're assuming that, but we might get a bit of lumpiness. So if we keep splitting here, as we get down to this, S3 covers 3 elements, S1 covers 2, and S2 covers 0 elements, whereas S covers 5 elements. So it's got lumpy because because things aren't distributed as evenly. So we actually have to deal with estimates of size when we split at this level. So this was 16 elements in total. But when we get down to the split arrays themselves, we're saying there's an estimate of 4 elements, but there might be more, there might be less. So that's why it's not as good as array list, but it's better than linked list. Okay, so I've got 5 minutes. So streams, in summary, is really quite a powerful framework. It provides a really compact and readable and performant way and less error-prone way to get work done. And it's something that you can look at, and if you want to use, you don't have to copy or reuse a stream interface if you don't want to. You could actually just copy the patterns of map, filter, flat map, and apply them to your own APIs as well. Don't just think of using stream if you don't want to, but copy the patterns that we've implemented. It's an easy path to parallelism, but it's not always the right thing to do. You should try and measure what's going on, and hopefully I've given some hints about that. And it's really deeply implemented in collections, and that's where a lot of the work has been, is to implement these in collections. And the key thing I hope I got across is that there's potential optimizations in the future if we look at how value types and arrays and inlining can be improved in the future. We can even get better performance going forward. Okay, so 4 minutes for questions. Okay, so the question was about how do you execute things in parallel. So we decompose into separate threads, and we operate on each thread sequentially over a subset of the source. And then we merge the results back up, like that decomposition tree I showed there. So essentially we're using fork join under the covers to split our problem up into multiple little problems and operate on them sequentially, and then merge the results back up. Should we take that offline, see if there's another question that people want to ask, and then I'll talk to you offline. Any more questions? Yes? Good question. Question was, any way to customize the number of threads you're creating? Yes, sort of. We use the fork join common pool underneath the covers, and the only way you can configure that is through system properties. So we're not providing any ability to tweak the parallelness of what's going on. And the reason is because we weren't sure what the right way to do it was without actually giving something that people are going to shoot themselves in the foot with. Good question. It actually gets quite detailed depending on what the type of stream is. You can have a stream that's infinite that essentially is an iteration, which is inherently sequential. And what you can do is you can take a prefix of elements, copy them into an array, work on that, take another prefix, work on that, and you can increase the prefix size as you go on and build it up. That's the way you do it out of iteration. There's more complex ways you can do it as well, but I'm not sure I want to get into that just right now. But that helps, I hope. And 2 minutes left, any more? Okay, I think we're done. Thank you very much.